Now, transfer our mic to her. She'll now speak directly to you about the session and today's topic. Thank you, everybody, for joining in. We hand over the mic to you now, ma'am.
Hi, everyone. I will say, first of all, good morning, good afternoon, and good evening to all of you, because here it is morning and there it is evening. And if I miss somebody from afternoon, yeah. So I hope your day is going good. And for especially people from India, I know that Saturday evening attending a lecture, yeah, it if you're interested in space, then it's going to be really good. And I welcome you and thank you for coming and attending my talk today on space weather in daily life. And and yeah, I must thank Propagation Institute for inviting me. And this is a really good initiative these people have taken, and you're doing a really good job, I think. And thanks a lot for inviting me. So let's start. So this is a picture of Northern Lights. Everyone might be knowing. So yeah, it's a beautiful picture. And we will start with the title itself. What is space weather? Space weather is the conditions in space which are caused by the activities in the sun and affecting our day-to-day activity. That's mainly technology. So what do sun do? Sun emits like solar wind, solar flares, coronal mass ejections. We will come to these in detail in the next slide. So I will just give an overview of what is space weather. So sun emits these particles, electromagnetic radiation masses, and they come and interact with our Earth's magnetic field and the upper atmosphere of Earth, which causes disruptions in our GPS navigation. Then there's communication or our power lines or even the spacecraft itself. So scientists are studying, continuously monitoring the space weather. It's like weather of our atmosphere. The weather here is directly affecting us, but the weather up in the atmosphere, that space weather, is affecting through the technology we are usually using. So scientists are continuously studying to understand this our space environment. So coming back to what do sun do? Sun emits like continuous outflow of plasma. Plasma is charged particles at higher temperatures from the sun's corona, and its speed is around 400 to 800 kilometers per second. It will take 1 to 3 days, but it is continuously emitting from the sun, so it is constantly coming and interacting with our Earth's magnetic field all the time. And we are in the flow of solar wind. And another thing is solar flare, which are sudden bursts of intense electromagnetic radiation, such as X-rays, radios, and UV rays. And those are also emitted from the sun's surface, but these are electromagnetic radiation, so they travel in the speed of light, which takes about 8 minutes, only 8 minutes to reach the Earth. And another thing is the coronal mass ejection. As the name suggests, it is from the corona, sun's corona, and it is a mass. It is actually a large cloud of magnetized plasma, that is plasma embedded with the sun's magnetic field. So as from the name itself, definition itself, we can find that there is a sun's magnetic field is coming towards the Earth, and Earth, as I said, Earth have a magnetic field, so they interact, and that causes geomagnetic storms, which we will talk in a bit. What are its effects on our space weather? Yeah, its speed is also 300 to 1,000 kilometers per second. So this also takes 1 to 3 days to reach the Earth. So these are 2 videos to show Sun-Earth interaction. I hope it's audible. I'm not going to show
Heat moves to the surface in huge eddies called cells. These electrical currents of charged
I'll just show the
sunspots
coronal mass ejection, which
the electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. And then the rubber band breaks.
that is the coronal mass which is being ejected, and it travels through the
Several billion tons of plasma
interplanetary
is hurled out from the sun.
medium. Just a moment. It will travel through different planets, and once it reaches Earth, we will see.
When the solar
Yeah.
storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks. Gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime.
So this is the nighttime aurora, and so you got an understanding of how the sun emits the CME or coronal mass, and then it travels through the interplanetary medium and interacts with our Earth's magnetic field, and how it creates aurora. But yeah, there is another, just a second, video which shows these are also, it is to show the large scale nature of the coronal mass ejection. It's not small, and it is so huge, and sometimes it might be we will just miss the coronal mass ejection, like the one here. You can see this one we got hit, but yeah, others are getting emitted in all directions from the sun, and this one is huge, but we missed it. Yeah, so that was about the sun-Earth interaction, but how or when did we come to know about the space weather and its effects? For that, we need to go back into the history. So in the early 1800s, Alexander von Humboldt was continuously monitoring our Earth's magnetic field using a compass needle in his office, and he saw that suddenly it's started just going up and down, and it just goes anywhere, and it just deflects. And that was coincided with the aurora on that day. So he coined the term magnetic storm. Later in the 1830s, Carl Friedrich Gauss and Wilhelm Weber built a precise magnetometer. So the magnetometer should be precise enough to detect these magnetic fields, because our Earth's magnetic field is so large, and the magnetic field, due to the space weather interactions, will be smaller, and for that we need to have better accurate magnetometers. So that was built in 1830s, and then in 1840s, one scientist called Edward Sabine correlated these magnetic disturbances with sunspot numbers, which are from where these coronal mass ejections happened from the sun. And that was the first time, okay, the sun and the disturbances causing in the Earth are correlated. That was found in 1840s. And then there was a very big event, or destructive event called Carrington event happened in 1859. Carrington was a scientist who observed the first solar flare, and then hours later, people saw in magnetometers that they also went off scale, and telegraphs were used at that time for communication. The people who were operating on the telegraphic equipments got shock, and some of the telegraph got fire. So, and even the aurora was seen all over the world. Not all over the world, but more in the equator side also. So this was also a link showing Sun and Earth's magnetic field relation. So yeah, the first thing we saw, or the visible proof of space weather, is aurora, as you see. So in the video, when the solar and Earth's magnetic fields interact with each other, particles from suns, this coronal mass ejection will move through the Earth's magnetic field, and then they precipitate in the polar atmosphere. So they cause these colorful lights, northern lights, or called aurora. And depending on the altitude or height at which these particles are precipitating, and the color of the aurora will be different, because the species or the atom or molecule present in that altitude will be different. Like here, which is the green, which is the most common aurora seen, it is from the atomic oxygen at 240 kilometers or lower. But if the oxygen, if the aurora, particles precipitated at a little bit higher orbit, higher altitude, then still it is oxygen, but it will give out a reddish color. And if we go below, like 96 kilometer or on that region, we have molecular nitrogen, which gives purple, and if it is even below that, then it gives blue colored auroras. But yeah, that's the good side of space weather. We could see beautiful auroras, but there are downsides too, which is our main topic today. It's space weather's impact on the technology. So we will go through each one of these. So how the power lines are surged, or the communication is affected in HF radio or in the satellite, and also in the collection of GPS navigation, or how it affects astronauts, or in the aviation industry, and lastly on the satellite track. So like we saw that during geomagnetic storms, this magnetospheric, the Earth's magnetic field and Sun's magnetic field interact, and they precipitate their particles into our atmosphere. And so these particles move in opposite directions and creates currents in the charged particles, I mean, in the upper atmosphere called ionosphere, or in the magnetospheric region, which is the whole magnetic field of Earth, the region dominated by that. So these currents are always there, but when these storms happen, we have more particles, charged particles, and which causes more currents. And this, when the currents are more, we have a time varying magnetic field. We know that when from Faraday's laws, that when the magnetic field is changing with time, then it can induce electric fields. So where do it induces electric field? In the Earth's crust, or in the Earth's crust is just below the surface. We have magnetized rocks and soil with different minerals with magnetic properties in the below our ground. And also we have power lines or pipelines carrying gas or electricity we have those things also. So wherever there is possibility of conductivity, this changing magnetic field will cause electric fields, which is sudden, and this causes a voltage difference between different places of Earth, and it again causes currents, which are called geomagnetically induced currents, which flow through our power lines and power grids or transformers, where it's like we need AC current, and these GICs are DC currents, which will cause sometimes the transformer gets heated or there is a voltage instability, and in some cases it goes into complete blackout of the regions. So there was a storm in 1989. The grids or power grids on Hydro-Quebec in Canada got collapsed in 19 seconds, and 6 million people were without power for about 9 hours. So the transformers were damaged even in the US at New Jersey too. So that was a huge storm, and its effects were so huge that it got the Canada place was completely in blackout for 9 hours. For overcoming these type of problems, we have real-time monitoring of the space weather, like how and when the solar flare or the coronal mass ejection is keep on coming, and there are modelers who keep on modeling Earth's conductivity and try to find if there is a difference or sudden changes happening and what to do with that. So there are many things scientists do and help with the power companies or electrical companies to keep their equipment safe. And the main National Oceanic and Atmospheric Administration is the one which monitors space weather and continuously providing us with the space weather alerts. So another topic or the effect of space weather on technology is the high frequency radio communication. So so this is an electron density profile of just look at one of this. We are not going into more details. So electron density profile in the atmosphere above 50 kilometers, which is the ionospheric layer. Ionosphere means the charged particles are at higher temperatures. That is, plasma is there in the atmosphere along with the neutral particles. So it has different layers where as we move up, the electron density is getting higher, D, E, F1 and F2 layers. And at the same time, it's not here, but we have neutral particles also whose densities keep on reducing as we move up in the altitude. So in how do we do radio communication? High frequency radio communication is through reflection from one station to the ionosphere, sending radio waves from one ground station to the ionosphere, and it gets reflected from E or F layer, and then it reflects to another ground receiver station. So that's the normal happening thing. And mostly in the D region, if the frequency of the radio waves are less, then they get absorbed in the D layer. So we need a optimum frequency, high frequency, that is in the 3 to 30 megahertz, which matches with the plasma's frequency here. Then only it will get reflected back to the ground. So it is used by transoceanic spacecraft, aircrafts, and in ships, and also in military and amateur ham radio and also in emergency responses during natural calamities or other problems which are in emergency. But during storm time, what happens to this radio communication? Like we said, for solar flare, when the X-rays come, this D region gets ionized, and then the absorption increases. So D region was, if you remember here, it was less ions here, but this got increased, and then the absorption of radio waves got increased. And also at the same time, we have a limited capacity or the highest usable frequency from the F region. Also, as the lower frequency itself or the higher frequency itself is getting absorbed in the D region, there will be blackouts on the day side. Day side means sunlit side. And then there are solar proton events, which we saw in the polar region, how the aurora is forming when the solar protons from the solar CME or solar wind get precipitated into the polar regions. They ionize more D and E region, and there also it happens absorption of the radio waves, and then near to the poles also we have blackouts. Like that for geomagnetic storms, also similarly it happens, and the fading of radio waves, high frequency radio waves happens, and all the usage by all these aviation, maritime, military, all will be affected by those. For this to not happen, or to mitigate these effects, what people do is they use frequency agility. That's they change the high frequency band to certain other bands depending on the how much D region is ionized and what is the permissible limit. And they will also have different pathways to communicate to the same place, from one ground to an optimum location in ionosphere, which gets reflected to another ground place. So they will use different paths, or they will just use more higher frequencies to communicate with the satellite, and then receive and transmit it to the ground station of their choice. And of course, there are real-time monitoring of what is always happening in the ionosphere. That's also done by the Space Weather Prediction Center at NOAA. They also keep on sending alerts on the HF radio communication too. And now when we come to satellite communication, for HF radios, it was in megahertz of radio waves which were getting reflected. But for satellites to pass through the ionosphere, the frequency should be very high. It should be in the microwave signals, which is in gigahertz. And so we send the microwave radiations from the ground station of requirement to the satellites, and then transmit it from there to the another ground station. So where it is used, it's for our TV, or for GPS, or for internet, remote sensing, in defense. It's used. This is the most used in our day-to-day. Yeah. Or similar to HF radio, like we saw it with how the solar energetic particles or the solar flares, how they are affecting the ionosphere. It's similarly affects satellite communication too. And also these energetic particles, which are affecting the ionosphere, they also affect the satellites in different ways, like they affect their electronics or their surfaces. So satellite getting the electrically shocked, and their components getting in different problems. So for that, we use like radiation is, we use electronics which are not affected by radiation. And also once you find out there is a problem, there are adaptive. That means it is instantaneously modulated to different signals, or multiple paths are used, or different backup satellites will be used. And of course, NOAA and SWIPSI are always forecasting, and there is real-time monitoring going, which keeps on giving alerts to companies for satellite communication. And yeah, then comes the similar to satellite communication. We use global positioning satellite, or GPS, at 36,000 kilometers. 20,000 kilometers. I think it's, 20,000 or 30. I'm sorry, I just missed it. Kilometers. And it also broadcasts timing and position signals. So that's how you know exactly at this point of time, up to millisecond precision. And this place with less than a meter or so, you know your exact position using GPS satellites. It's the similar way that receivers on the ground calculate the location from the signal which is traveled from the transmitter to the satellite, GPS satellite, to the receiver station. Yeah, of course, it passes through the ionosphere. So whatever we discussed earlier will affect here too. So these are used in aviation, ships, and also in agriculture, precision farming, and also in magnetic surveys and exploration, and also in emergency services. These GPS collections are used. Yeah, like we said, these solar flares causes sudden X-ray and UV bursts in the ionosphere, which increases ionization, and then our signals could delay. Also, the geomagnetic storms, like we discussed, it causes irregular electric fields, and they also disturb the ionosphere, and large electron contents are being deposited, which again causes problems in the signal. And another thing is scintillation, which is the rapid amplitude or phase fluctuations of the electromagnetic radiation we are sending. And this is caused by day-night variation of how the ionosphere is getting formed. During daytime, we have sunlight, and ionosphere has more ions, and during nighttime, there is less. There is no source. There is no sunlight to create the ions, and thus there is an instability which causes amplitude or phase fluctuations, and this can also affect our GPS signal. Yeah, all these can cause positional errors, timing errors, or total loss of the signal. And in terms of aviation and astronaut safety, the particles from the sun, which raise the radiation exposure on high latitude flights. So sometimes when there is a storm, airlines are rerouted to lower latitudes. And for astronauts in International Space Station, or if they are going beyond ionosphere to either moon or in future in Mars, there are different effects like biological effects, this radiation sickness, and there are long-term probability for cancer and cataracts, and their DNA and cell can damage and impaired nervous system and immunity. Also in operational risks, the spacecraft's electronic upsets, the ones which we discussed for communication, communication and navigation links are lost, so how they will communicate back to Earth. And they are in danger during extravehicular activities like doing spacewalk And their solar panels and sensors could also be degraded. So protecting technology also means we have to protect people too. So the space weather affects people too, even though it's less and in number and it's rare. It is important to keep on finding resources and alerts to keep on looking after the people and technology we are depending on. And another thing of space weather effect is the satellite drag, which is when the geomagnetic storms happen, there is extra energy in the atmosphere, which causes heating of the atoms and molecules there, and it causes the atmosphere to expand. Like I said, as we normally as we move up in the altitude, the our thermospheric density or the atmospheric density keeps on reducing. But when the atmosphere expands during a storm, the lower atmosphere with higher density will be now in the higher altitudes. So this dense air increases drag on satellites. So drag is similar to any resistive force moving for a moving object in a fluid, since it is mainly affected for the satellites in low Earth orbiting, that is between 200 to 1,000 kilometers. So here you can see that when the orbit has no drag, the satellite is supposed to move like this, but when the drag is there, the satellite is moving in this direction, which is not what we wanted. So yeah, that's what happens. Like in consequence of a geomagnetic storm, it gradually the altitude loss happens, and it will try to re-enter to the Earth, where there is more atoms or neutral particles, and it may risk to burn up the satellite. And of course, when there is more neutrals present, for the satellite to keep up to the altitude of desired altitude, it will use up the fuels, and thus the lifetime of satellites will be lesser. Also, there is mission risk, like it can deorbit the newly launched satellites, and we will have difficulty tracking where these satellites will be moving, and it can cause other problems, like if we do not know the orbits, it can collide with other satellites too. So there was I will come to that. For that, there are many ways to avoid these. Like we said, the space weather is always monitored by the NOAA or NASA people, and people are always keep on modeling the density in neutral atmosphere using real-time data too. Our group is working on NASA's space weather operation readiness development, where in 5 years we are planning to develop a model connecting the input from sun to the magnetosphere and ionosphere and the thermosphere, where the neutrals are present, and connecting all different types of models and trying to model it to predict the thermospheric density during geomagnetic storms. And so other mitigation techniques are, you keep on raising the orbit before storm. Also even during there is no storm, the satellite it's 3 to 4 times raised their orbit during a whole year. And also during storm time, you need to do it like 2 to 3 times in a week. Then you can track orbits frequently and correct for the unexpected decay, and then maintain the fuel margin for drag compensation, avoid very low altitudes during solar maximum. Solar maximum is when the sun is most active, and it creates like very it generates a lot of CMEs and other events we already discussed. So we should always rely on the International Space Weather Alerts and keep an eye on it. So there was an event in 2022, the Starlink satellites were from SpaceX launched like 49 satellites, and there was a moderate geomagnetic storm, and it increased the thermospheric density by 50% at 2 ton kilometer, and this made it like 40 were lost to drag. So that was a very huge loss, and we need to keep on monitoring it. So we discussed all the effects of space weather and on technology and how it is mitigated, but why it matters now also. If we have found many solutions, why it matters. That's because if you look at this, you can see in 1957, the satellites were less than 10. And as we move from 1950s to 2000s, it has come to hundreds of satellites. And in the recent years, this is in 2023, around 9,000 satellites. And currently it is 12,000 to 16,000 satellites are in orbit. So our use of satellites keep on increasing, and we are relying on the technologies which depend on these satellites. And like we said, the communication through HF or the satellite navigation or the communication through satellites or other things are also keep on increasing. You can see different satellites which are used for in the heliophysics. So these are all used to learn about our space weather. So that's why it matters that space weather links the sun, space, and Earth. So understanding it helps protect the technology and people that our modern world depends on. Thank you, everyone. And I'm happy to take any questions. And if I could not answer, or if you did not get a chance to ask a question, please feel free to reach out to me through this email. Thank you.
Thank you, ma'am. Thank you so much for this amazing session. We'll start with the questions. People who wish to ask questions to ma'am directly, you can raise their hands. We'll pick out the people, and you can open your mic and then ask the questions. Till then, we'll take some questions from the chat and read them out to you, ma'am, and you can answer them. Okay, let me see. Abhishek asks, how did scientists in the early 1800s measure geomagnetic activity without advanced instruments?
1800s, like I said, it was first using compass and just looking at the aurora. They just compared it and correlated the relation. But after that, when the magnetometers were made, that is when the magnetometer started. Magnetometers started recording the magnetic field from these activities, mostly near to the equator or near to the auroral regions where we have auroral electrojets, where the aurora happens. We have the currents also cause magnetic field deflections, which are not normally seen. We have a pattern in the Earth's magnetic field, which is happening in the day-to-day.
Nice. Yuvraj asks, how exactly do they precipitate in the atmosphere? It's in some context.
Okay. I understood. I think I showed it in the video. Let me know if my slide is still visible.
Yes, ma'am, it is.
The particles get connected through the Earth's
Speeds.
magnetic field, like here. Yeah, this process of solar magnetic fields and Earth's magnetic field connection is called reconnection. And when this happens, this is called particle precipitation, where the Earth's magnetic field and Sun's magnetic field got connected. There is a reconnection happening here too. It transfers its particles to, along with the magnetic field, it transfers its particles to the Earth's magnetic field, and then these particles travel. Charged particles have a tendency to go with the magnetic field. Anything when a force acts on it, so this magnetic field acts as a force, and this charged particles like electrons, they will gyrate along the magnetic fields, and they just come down. And when they reach a place where there are enough neutrals, then that is another force, that is collisional force, which causes them to interact with these neutrals and the coming charged particles to interact. And it just goes into another chemical reaction of to positive and negative charges, and they just lose it there. When this happens, the neutral atoms get excited and it releases energy, and that's how the colors are formed.
Mansi has another question that says, what measures do agencies like ISRO and NASA take to protect satellites from high energy particles during solar flares?
I'm not sure of ISRO, but I think for NASA in general, NOAA is it was about solar flares, right?
Yes.
Yeah, increasing. Yet it's in general they create like I have discussed it here. They use electronics which are less affected by these radiations, and also try to send the the question was, sorry, to protect
the satellites from solar flares.
Okay, mostly use radiation hardened electronics, and I'm not sure of other things which are being done.
Okay, I'll start with the next question. Atufa has another question that says, scientists are working to replicate the sun's plasma for clean and limitless energy through projects like South Korea's K-Star reactor, China's East reactor, and France's West reactor. I want to know if there are any possible negative effects of these experiments on Earth's atmosphere.
So they are trying to replicate sun's plasma for clean and
limitless energy.
Okay, I do not think there should be an effect if it is in a productive environment, laboratory environments. There shouldn't be much problem with the outside world. But I do not know of actual problems which can come. I'm sorry.
Right. I'll move on to the next question. Yuvraj has, do Faraday cages help in protecting from these? Also, how do then?
ISS had certain, I forgot to put it here, but ISS definitely have these radiation deflecting equipments and other equipments where it is not affected. Of course, their satellites are covered with radiation, not affecting electronics and everything. and then their suit they are wearing is also made protective from this, and there are things like it can deflect some of the radiations from the there are advanced equipments for ISS specifically to deal with this, but may not be because there are people involved, but it may not be the case with other satellites.
All right, we'll move to the next question. Yuvraj has a question that says, wait, so if we raise the orbit during storm, doesn't it make the satellite more susceptible to the storm particles since it'll have less magnetosphere around it?
It's not like that. Satellite stays in like LEO. If it is in LEO, that is from 200 to 1,000 kilometer, or in MEO, 20,000 kilometers, or above that in geostationary 35,000 kilometers. In those altitudes, the satellites are always there, and when the particle storm happens, the like I said, thermosphere is expanding. But if we increase the altitude of the satellite, then they are in the same condition they were earlier. Maybe it had a just assume like X electron density was there at 400 kilometers, and then it increased to X into 10 raised to 2. And then if we move the altitude by some amount, and then we reach, since the atmosphere expanded, now the place where the satellite is have only X electron density, then it doesn't affect that negatively.
Okay, great. The next question comes from Bayman. Can we predict when aurora will be visible?
Yes, it is being constantly predicted from when the coronal mass ejection happens in the sun, or when the solar flare is happening, or other events which happen. The NOAA, National Oceanic and Atmospheric Administration, they are keeping an eye out on the sun all the time. From even our ISRO have a satellite now, Aditya L1, you might all know. So like that, different satellites are placed at an L1 point. It is the point, it's a Lagrangian point where the forces from sun and earth are canceling out each other. So at those points, we have satellites, and when there is an event happening in sun, NOAA keeps an eye on it, and they just give the prediction alerts all the time. It's continuously monitored. But for solar flares, it's a bit tricky. Like, it just takes 8 minutes to reach here. So then it becomes tricky. But for others, which it takes 1 to 3 days, then it is totally fine. And we get all the time alerts for aurora. And there are, if you go to NOAA SIPSI's website, you can email me if you did not find the website. You can always keep on see where the aurora will happen, or how much spread it will be having.
All right, I got a bit disconnected. And the next question, let me read it out. Okay, I don't have any more questions. I got disconnected. Anybody has any questions that that they want to ask directly to ma'am? They can raise their hands up, and we'll ask the questions directly to ma'am. Anybody in the queue? Yuvraj, you have any questions directly? Seems like okay, Yuvraj has it. Let me just. You can open your mic.
Hello, can you hear me now?
Yes, yes.
Good evening, ma'am.
Yeah, good evening, Yuvraj.
Good ma'am. I'm Yuvraj, and I had one question regarding your field.
Mhm.
It's about approaching the field on how you get to this field. Some of my friends are doing geology right now,
Mhm.
and they also really like physics, but they could not get a physics subject in their degree for some reason.
Okay.
And I asked them to join this session. They are with me right now.
Okay.
And on their behalf and also on my behalf, I wanted to ask, how could somebody go into these type of sciences without a physics subject in their bachelor's, just on the basis of geology? Like, is it possible to go there?
I'm not fully sure, but I know that in maybe not on Earth, but you can do such studies on planetary other planets. So that comes under maybe Jupiter's aurora or all those things will also be considered for geology students too. That's my understanding, but maybe I can dig up more and give you more information uh, in case you're interested more. I can look into that.
That would be wonderful. I will email you if you do not mind.
Yeah, sure, sure.
All right. Thank you, ma'am.
Thank you, Yuvraj. Somebody else wants to raise their hand and ask the question? Not please give notes. Okay. Seems like not a lot of people are raising their hands. We'll continue with the chat questions. SK Sahid again asks, he has to clarify something about the space debris thing. How does space debris affect the space weather? If it does not have a negative effect, what are the steps to reduce the debris?
Yeah, this is a very ongoing research going on in our field where, yes, definitely space debris affect other satellites and they it's all over our space and some of the debris which are less than 10 centimeter in size they cannot be even detected and at those altitudes they are moving at very high speed and if they come in contact with another satellite then the satellite may even get destroyed. So people are continuously monitoring the space debris, which are more than 10 centimeter in size, because those are the only ones detectable, and continuously keep on track of their orbits, where they are flying, and everything. So that's an ongoing research where now people are also using AI to keep track of these and trying to find like sometimes if you can bring down the space debris to the lower altitudes where there is more neutral density they can burn up and they are destroyed. So that's a very mostly approached technique used even for satellites which are now not usable. If you can track them and bring it down to the lower atmosphere, not definitely not below 200 kilometer, then it will burn up on its own. And that's something people always do. Now, other research are going on, even without bringing them down this much. What can we do? That's an ongoing research. Yeah, of course, for space weather, I think the question for space weather too. Yeah, when the storms happen and when the thermospheric density increases, if the space debris is in those altitudes, even without bringing them down, they can get flamed up. So that's a good thing, and even though it's not a good thing for most of our convenient technologies, but yeah, that's a good thing for space debris if they are present. Will burn up there.
Great. Tanisha has a question that she wants to ask directly. Tanisha, you may open your mic and go ahead with the question. Are you there, Tanisha? Yeah.
Yeah, a very good evening, everybody. Good evening, ma'am. It's a great privilege to have you here today's evening. And my question is about the aurora only, that you have focused more. That is it necessary that only the solar fumes are responsible for the emission of the aurora every time, or there are some other phenomena for the same?
Yeah, you need to have some charged particles to precipitate, and it's mostly, as far as my knowledge, solar energetic particles are the ones who precipitate into the polar atmosphere and creates aurora.
Okay, ma'am. Okay, okay. Thank you so much.
Thank you, Tanisha.
Thank you, Tanisha. Anybody else wants to raise their hand? Till then, a few questions from the chat. Satya has a question. Is the red aurora caused by high altitude atomic oxygen rarely seen from the ground because it's higher up? Or is it simply less common to have the energy conditions that can create it?
It's the second one. It is. You need to have energetic particles of those range and precipitate at those altitudes to create the aurora in red color. So yeah, it is this. It is less common to have energy condition.
Hmm. Okay. Tarun has a question that there's a concept that these satellites have created an artificial barrier to these solar activities, whether it is true or not.
I'm not equipped to answer that question. I do not know.
Uh, all right, that's the end of the questions. Thank you so much, ma'am, for answering so many questions, for solving people doubt, and such a wonderful session. We'll start with the ending of the session. Uh, okay, is there another question? Artificial, like okay, okay. I will start with the end of the session. Thank you so much, ma'am. We are extremely grateful that you came here to address the session and gave you valuable knowledge. We are extremely grateful for the people who came here to address and ask questions. We we would like for you to open your cameras so that we can take a quick picture, so that it becomes a sort of a memory, and we can have an understanding that we did attend this session. Okay, people, you must open your cameras. Let me take the picture. Okay, thank you, everybody. Thank you for coming here. We are excited for people who are in vendor school. We are excited that tomorrow classes will start. Thank you so much for attending the session. We will end with today's session right now. Thank you so much, ma'am, for coming in here. We'll end our session today. Thank you. Thank you, everybody. You may.
Thank you, everyone, and thank you, Propagation.
Thank you. Thank you, ma'am. See you tomorrow, you batch.